In this example, we're still trying to design a digital logic device. It's just that now we're trying to do it based on a truth table rather than based on a Boolean algebra expression. So remember that anytime you're faced with a truth table, first of all, verify that all 8 rows are there if there are 3 variables, 4 rows if there are 2 variables, or 16 rows if there are 4 variables, and then look at the outputs. In this case, I can see that only 2 of the rows have an output of 1. So there's an output of 1, and there's an output of 1. I'm going to identify what are the products that correspond to those 2 rows. So you can see here I have A is 0, so I get not A, and B is 0, so I get not B, and then C is 1, so I get C. Here I have A and not B and C. And so I can write an expression for F. F is just the sum of those 2 terms. So it's going to be not A and not B and C, or A and not B and C. Now when I look at that, I can see that that's going to be sum of products. It's always sum of products when it comes from a truth table. So I'm going to have 2 products. Here's product number 1, that'll be an AND gate. Product number 2, that'll be an AND gate. So I need 2 AND gates, each with 3 inputs. 1, 2, 3, 1, 2, 3. And then those AND gates always feed into a single OR gate. And here, because there are only 2 products, there's only 2 inputs to the OR gate. Those 2 inputs to the OR gate trace back to the fact that there were two products in the equation, which trace back to the fact that there were only 2 rows in the truth table that contained a 1. Now we need to fill in the inputs here. So I'm going to have A, which is going to go through an inverter. That'll go into this first input. B going through an inverter. That goes into this input, and then just straight up C goes into the third input. I know that A needs to go into the second input here, and then not B, so I'm going to grab it after the inverter, and then and C. So I'm going to grab C from right here, and there's my completed solution. Not as bad as some, but could definitely be better. Let's let that rest, and then let's look at part B. Please use Boolean algebra to minimize the complexity of the solution and redraw the circuit. Okay, so I'm going to zoom out here so we can see both the first part and the second part. F is equal to not A and not B and C, or A and not B and C. When I look at that, I can see that there is a not B and C that can be factored out of each term. So there is not B and C, and coming out of the first product, I have not A. Coming out of the second product, I have A. Not A or A becomes 1. Anything ANDed with 1 just stays itself. So therefore, F is equal to not B and C. So remarkably, there's only 1 product here. So when we say sum of products, there really isn't a sum in this case because there's just a single product. We can just write a single AND gate. We're going to need an inverter to generate B, and C is going to come in uninverted. So there is B, that makes that B bar. Here is C, and that is F. So you have your choice. You can either have the more complex solution that is shown up here, or you can have the much simpler solution that is shown here. Both of them will implement the same solution or implement the same truth table, but obviously the one in part B will do it more efficiently.